amp interrupting rating, or AIR, indicates a panel's ability to withstand fault currents. A 10 kIR home line panel may be sufficient for a 4,200 square foot church with typical loads. If there are anticipated high fault currents or sensitive equipment, square D panels with a 22 kIR may be preferable. Installing electrical panels in a classroom is generally not prohibited by the National Electrical Code. Ensure the panel is accessible and protected from damage. Provide adequate space for operation maintenance and potential expansion. For a 4-ton air conditioning unit, a general rule of thumb is to use number 10 American wire gauge wire for each unit. The current per ton for a typical 4-ton air conditioning unit is approximately 16 amps. According to National Electrical Code Section 310.15, for convenience plugs, the neutral is not counted toward the current carrying capacity of the neutral conductor. For fluorescent lighting, the neutral is counted toward the current carrying capacity of the neutral conductor. For a double oven installation, the box should be installed at the level of the oven's connection point, approximately 42 inches above the floor. Assuming a typical double oven configuration with a total wattage of 3,500 watts, number 8 American wire gauge wire would be sufficient. Most double ovens require only one electrical box with 2 circuits, one for each oven. The size of the transformer depends on the total load requirements of the church, including future expansion plans. An electrician should calculate the load and determine the appropriate transformer size. A detailed panel schedule should be created to indicate the circuit breakers, ampacities, and loads for each panel. All panels and circuits should be properly labeled for easy identification. A thorough site survey is recommended to assess the existing conditions, electrical needs, and potential challenges. Several factors influence the appropriate American wire gauge wire size for an air conditioner. These include the air conditioner's current draw, the ambient temperature, the wiring method used, and the applicable codes and standards. To accurately determine the wire size for a 4-ton air conditioner, begin by consulting the unit's nameplate, which lists the minimum circuit ampacity or maximum overcurrent protection required. This information is crucial for selecting the correct wire size and breaker. Next, refer to National Electrical Code Table 310.15b16, which provides ampacities for conductors based on their insulation type and temperature rating. Ensure the wire's ampacity meets or exceeds the air conditioner's minimum circuit ampacity. Correction factors for ambient temperature must be considered. If the ambient temperature exceeds 86 degrees Fahrenheit or 30 degrees Celsius, the wire's ampacity must be derated according to National Electrical Code Table 310.15b2. This derating accounts for the reduced heat dissipation at higher temperatures. Adjustment factors for the number of current carrying conductors in a raceway or cable must also be considered. If multiple conductors are bundled together, their ampacity must be adjusted per National Electrical Code Table 310.15b3. This adjustment prevents overheating due to the close proximity of conductors. The wiring method, such as conduit or cable, affects the allowable ampacity. Ensure the chosen wiring method is suitable for the environment and complies with local codes. Common wiring methods include rigid metal conduit, electrical metallic tubing, and non-metallic sheath cable. Always adhere to local electrical codes and regulations. These codes may impose additional requirements or restrictions on wire sizes and installation practices. Consult with a qualified electrician or electrical inspector to ensure compliance. The current draw of the air conditioner is a critical factor in determining the appropriate wire size. The unit's nameplate provides this information, typically listed as the minimum circuit ampacity. For a 4-ton air conditioner, the current draw usually falls within the range of 15 to 20 amps per ton, resulting in a total current draw of 60 to 80 amps. It is essential to use the exact value from the nameplate for accurate wire sizing. Ambient temperature plays a significant role in wire ampacity. As the temperature increases, the wire's ability to dissipate heat decreases, requiring a reduction in its ampacity. National Electrical Code Table 310.15b2 provides correction factors for various temperature ranges. For example, if the ambient temperature is 104 degrees Fahrenheit or 40 degrees Celsius, a correction factor of 0.88 may apply, reducing the wire's allowable ampacity by 12%. The wiring method significantly affects the wire's ability to dissipate heat. Conductors installed in conduit have different ampacity ratings than those installed in open air. National Electrical Code Tables 310.15b16 and 310.15b17 provide ampacity values for different wiring methods. For example, a number 10 American wire gauge copper conductor with THHN insulation has an ampacity of 30 amps in free air, but only 20 amps when installed in conduit. National Electrical Code tables and guidelines are essential for determining wire sizes. These tables provide ampacity values for various wire types, sizes, and installation conditions. Always consult the latest edition of the National Electrical Code to ensure compliance with current standards. Grounding is a critical safety measure. Ensure the air conditioner is properly grounded according to National Electrical Code Article 250. A separate grounding conductor should be run with the circuit conductors to provide a low impedance path for fault current. Overcurrent protection, such as circuit breakers or fuses, is essential to protect the wiring and equipment from overloads and short circuits. The overcurrent protection device should be sized according to the air conditioner's nameplate and National Electrical Code requirements. Voltage drop can affect the performance of the air conditioner. Calculate the voltage drop to ensure it remains within acceptable limits, typically no more than 3%. If the voltage drop is excessive, increase the wire size to reduce the resistance. Inspection and maintenance are crucial for ensuring the continued safe and reliable operation of the electrical system. Regularly inspect the wiring, connections, and equipment for signs of damage or wear. Perform routine maintenance, such as tightening connections and cleaning components to prevent problems. Consider future expansion when sizing the wiring and equipment. If the church plans to add additional air conditioning units or other electrical loads in the future, increase the wire size and panel capacity accordingly to avoid costly upgrades later. When calculating the neutral load for fluorescent lighting in a 120/240 volt, 3-wire system, the neutral conductor carries the unbalanced current. In a balanced 3-wire system, the neutral current is ideally zero because the current from each of the two hot legs is equal and opposite, effectively cancelling each other out. However, in reality, loads are rarely perfectly balanced, resulting in some current flowing through the neutral. Firstly, determine the total load on each hot leg. Add up the wattage of all the fluorescent lights connected to each leg. For example, if one leg has 10 40-watt lights and the other has 8 40-watt lights, the calculations will differ. Secondly, calculate the current on each leg. Use the formula current equals power divided by voltage, or I equals P divided by V. Assuming a voltage of 120 volts, for the leg with 10 40-watt lights, the total power is 400 watts, so the current is 400 watts divided by 120 volts, which equals 3.33 amps. For the leg with 8 40-watt lights, the total power is 320 watts, so the current is 320 watts divided by 120 volts, which equals 2.67 amps. Thirdly, calculate the neutral current. The neutral current is the difference between the currents on the two hot legs. In this example, the neutral current is 3.33 amps minus 2.67 amps, which equals 0.66 amps. This neutral current must be taken into account when determining the size of the neutral conductor. Fourthly, check for harmonic currents. Fluorescent lights, especially those with electronic ballasts, can generate harmonic currents. These are multiples of the fundamental frequency, which is typically 60 Hz. Odd harmonics, such as the 3rd, 5th, and 7th, are particularly problematic because they add arithmetically in the neutral conductor rather than cancelling out. This can cause the neutral conductor to overheat if it is not properly sized. Fifthly, use a true root mean square ammeter to measure the actual current in the neutral conductor. This is the most accurate way to determine the neutral current, especially if there are significant harmonic currents. A true root mean square meter measures the effective value of the alternating current taking into account any harmonic content. Sixthly, size the neutral conductor appropriately. The neutral conductor must be sized to carry the maximum neutral current, including any harmonic currents. Consult National Electrical Code Table 310.15b16 for the ampacity of different conductor sizes. Also, consider any directing factors for ambient temperature or the number of current-carrying conductors in a raceway. Seventhly, consider future expansion. If there is a possibility that more fluorescent lights will be added to the circuit in the future, increase the size of the neutral conductor accordingly. It is better to oversize the neutral conductor than to undersize it, as this will prevent overheating and ensure the safety of the electrical system. Eighthly, ensure proper grounding. The neutral conductor must be properly grounded at the service entrance to provide a low impedance path for fault current. This will help to protect against electric shock and prevent damage to equipment. Ninthly, consult a qualified electrician. If you are unsure about any aspect of calculating the neutral load or sizing the neutral conductor, consult a qualified electrician. They will be able to perform the necessary calculations and ensure that the electrical system is safe and compliant with all applicable codes and regulations. Tenthly, document your calculations. Keep a record of all calculations and measurements used to determine the size of the neutral conductor. This will be helpful for future reference and will also be useful if you ever need to troubleshoot any problems with the electrical system. To select a suitable panel for the church, firstly, determine the total load. Calculate the total electrical load for the church, including lighting, receptacles, heating, ventilation, and air conditioning, and any other equipment that will be connected to the electrical system. Use the nameplate ratings of all equipment to determine their power consumption. Secondly, determine the service size. The service size is the total amount of power that the electrical service can deliver to the church. This is typically specified in amps. The service size must be large enough to handle the total electrical load of the church. Thirdly, select a panel with an appropriate ampacity rating. The ampacity rating of the panel must be equal to or greater than the service size. This will ensure that the panel can handle the total electrical load of the church without overheating. Fourthly, select a panel with an appropriate number of circuits. The panel must have enough circuits to accommodate all of the electrical loads in the church. It is also a good idea to have some spare circuits for future expansion. Fifthly, consider the interrupting rating of the panel. The interrupting rating is the maximum fault current that the panel can safely interrupt. The interrupting rating must be high enough to handle the available fault current at the service entrance. The available fault current is the amount of current that would flow in the event of a short circuit. Sixthly, consider the type of panel. There are two main types of panels, main lug only and main breaker. A main lug only panel does not have a main breaker. Instead, the service conductors are connected directly to the main lugs of the panel. A main breaker panel has a main breaker that disconnects all of the circuits in the panel. Seventhly, consider the location of the panel. The panel should be located in a dry, accessible location. It should also be protected from physical damage. Eighthly, consider the cost of the panel. The cost of the panel will vary depending on the ampacity rating, the number of circuits, the interrupting rating, and the type of panel. Ninthly, consult with a qualified electrician. A qualified electrician can help you select the appropriate panel for your needs. They can also ensure that the panel is installed safely and correctly. Tenthly, consider future expansion. If there is a possibility that the church will need more electrical power in the future, select a panel with a higher ampacity rating and more circuits than is currently needed. This will save you the cost and trouble of replacing the panel later. The location of electrical panels in a building is governed by several national electrical code regulations to ensure safety and accessibility. National Electrical Code Section 110.26 outlines the requirements for working space around electrical equipment. This section mandates that sufficient space be maintained around electrical panels to allow for safe operation and maintenance. The minimum depth of the working space varies depending on the voltage of the equipment and the conditions on the opposite side of the working space. For example, for equipment operating at 150 volts to ground, a minimum working space depth of 3 feet is required if there are exposed live parts on both sides of the working space, or if there are exposed live parts on one side and grounded parts on the other side. The minimum width of the working space should be at least 30 inches or the width of the equipment, whichever is greater. The minimum height of the working space should be 6 feet 6 inches or the height of the equipment, whichever is greater. National Electrical Code Section 240.24 addresses the accessibility of overcurrent devices. This section states that overcurrent devices, such as circuit breakers and fuses, must be readily accessible. Readily accessible means that the overcurrent device is capable of being reached quickly for operation, renewal, or inspection without requiring those to whom ready access is requisite to climb over or remove obstacles or to resort to portable ladders, chairs, and so forth. Overcurrent devices must not be located where they will be exposed to physical damage. National Electrical Code Section 312.8 permits enclosures for switches or overcurrent devices to contain splices, taps, or feed through conductors. However, the enclosure must not be filled to more than 75% of its cross-sectional area, and all conductors, splices, and taps must be permanently identified. National Electrical Code Section 408.3 addresses the installation of switchboards and panel boards in damp or wet locations. This section requires that switchboards and panel boards be protected from the weather and installed in a manner that prevents moisture from entering the enclosure. This can be accomplished by using a weatherproof enclosure or by installing the panel board in a location that is not subject to dampness or wetness. National Electrical Code Section 408.5 addresses the illumination of switchboards and panel boards. This section requires that sufficient illumination be provided to allow for safe operation and maintenance of the equipment. The illumination must be adequate to allow workers to read the panel board labels and to operate the switches and circuit breakers. National Electrical Code Section 408.7 addresses the arrangement of switchboards and panel boards. This section requires that switchboards and panel boards be arranged in a neat and workmanlike manner. The conductors must be neatly bundled and supported, and the equipment must be labeled for easy identification. National Electrical Code Section 408.36 addresses the available fault current marking. This section requires that all switchboards and panel boards be marked with the available fault current at the service entrance. This marking provides information to electricians and other qualified personnel about the maximum fault current that the equipment is capable of withstanding. When selecting the ampacity interrupting rating of a circuit breaker, several factors need to be considered to ensure electrical safety and compliance with the National Electrical Code. The ampacity interrupting rating, or AIR, of a circuit breaker is the maximum fault current that the breaker can safely interrupt without being damaged or causing an electrical hazard. Firstly, determine the available fault current. The available fault current is the amount of current that would flow in the event of a short circuit at the point where the circuit breaker is installed. This can be calculated using various methods, including short circuit studies or simplified calculations based on transformer size and impedance. The available fault current is typically expressed in amps. Secondly, select a circuit breaker with an AIR equal to or greater than the available fault current. The AIR of the circuit breaker must be equal to or greater than the calculated available fault current. This will ensure that the breaker can safely interrupt the fault current without being damaged or causing an electrical hazard. If the AIR of the circuit breaker is less than the available fault current, the breaker could fail to interrupt the fault, leading to a fire, explosion, or other serious electrical hazards. Thirdly, consider the voltage rating of the circuit breaker. The voltage rating of the circuit breaker must be equal to or greater than the voltage of the circuit. This will ensure that the breaker can safely interrupt the voltage without being damaged. Fourthly, consider the type of circuit breaker. There are several different types of circuit breakers, including thermal, magnetic, electronic, and solid-state breakers. Each type of breaker has its own advantages and disadvantages. Thermomagnetic breakers are the most common type of breaker and are typically used in residential and commercial applications. Electronic breakers offer more advanced features, such as adjustable trip settings and remote monitoring capabilities. Solid-state breakers are the most advanced type of breaker and are typically used in high-current applications. Fifthly, consider the listing and labeling of the circuit breaker. The circuit breaker must be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or Canadian Standards Association. This will ensure that the breaker has been tested and meets applicable safety standards. Sixthly, consult with a qualified electrician. A qualified electrician can help you determine the available fault current and select the appropriate circuit breaker for your application. They can also ensure that the breaker is installed safely and correctly. Seventhly, document your calculations. Keep a record of all calculations and measurements used to determine the available fault current and select the circuit breaker. This will be helpful for future reference and will also be useful if you ever need to troubleshoot any problems with the electrical system. Eighthly, consider the impedance of the transformer and conductors. The impedance of the transformer and conductors will affect the available fault current. The higher the impedance, the lower the available fault current. Ninthly, consider the length of the conductors. The length of the conductors will also affect the available fault current. The longer the conductors, the lower the available fault current. Tenthly, consider the conductor size. The conductor size will affect the available fault current. The larger the conductor size, the higher the available fault current. Several key electrical codes relate to the installation of outlets for electric ovens. The National Electrical Code provides comprehensive guidelines to ensure safety and proper functionality. Firstly, National Electrical Code Section 210.8 covers ground fault circuit interrupter protection for personnel. While not always required for electric ovens themselves, it's crucial to check local codes, as some jurisdictions may mandate ground fault circuit interrupter protection for outlets serving kitchen appliances. Secondly, National Electrical Code Section 210.52 addresses receptacle outlets in dwelling units, including kitchen areas. Although this section primarily focuses on general-purpose receptacles, it underscores the importance of proper placement and accessibility of outlets in kitchens. Thirdly, National Electrical Code Section 220.55 provides guidelines for calculating the load for electric ranges and ovens. This calculation is essential for determining the appropriate circuit size and wire gauge for the oven outlet. The standard method allows for a demand factor to be applied, which reduces the calculated load based on the assumption that the oven will not operate at its maximum rated power continuously. Fourthly, National Electrical Code Section 250.130 outlines the requirements for grounding the oven outlet. Proper grounding is critical for safety, as it provides a low impedance path for fault currents, reducing the risk of electric shock. The grounding conductor must be connected to the equipment grounding terminal in the outlet box and to the grounding electrode system of the building. Fifthly, National Electrical Code Section 400.8 details the permissible uses of flexible cords and cables. Electric ovens typically require a dedicated circuit with a properly sized conductor and a suitable outlet. Flexible cords are generally not permitted for permanent wiring of appliances like ovens. The connection between the oven and the electrical supply should be made using approved wiring methods, such as non-metallic sheathed cable or conduit. Sixthly, National Electrical Code Section 422.16 provides specific requirements for the installation of electric ranges and ovens. This section covers topics such as the support of the appliance, the clearance from combustible materials, and the proper connection to the electrical supply. It emphasizes the importance of following the manufacturer's instructions for installation to ensure safety and proper operation. Seventhly, National Electrical Code Section 110.3 mandates that electrical equipment be installed according to the manufacturer's instructions and within its listed or labeled ratings. This requirement underscores the importance of reviewing the oven's installation manual and adhering to the specified electrical requirements, including voltage, amperage, and wiring methods. Eighthly, National Electrical Code Section 314.27 provides guidance on the installation of outlet boxes. The outlet box used for the oven connection must be of the appropriate size and type to accommodate the wiring and the receptacle. It should be securely mounted and properly grounded. Ninthly, National Electrical Code Article 210 covers branch circuits, including the requirements for the number of circuits, the ampacity of the conductors, and the overcurrent protection. The electric ovens typically require a dedicated 240-volt circuit with a minimum ampacity of 30 amps or more, depending on the oven's power rating. Tenthly, local amendments to the National Electrical Code may exist and should be consulted. Local jurisdictions may have additional requirements or restrictions on the installation of electric ovens and their outlets. Always check with the local electrical inspector or building department to ensure compliance with all applicable codes and regulations.